So if you were to stand in the snow with no jacket, no hat, no scarf, you lost one glove, and it's starting to get dark, it's starting to get cold, how would your body react? Can you maybe show me how you think your body would be moving? Yeah, so you'd be doing this, you might start shivering, you might even start dancing if it gets really cold, and that's because you are, and we are as mammals, endothermic, which endo means inside, means we generate our body heat from within our bodies. And we try to keep it inside us, and that is because we can only function at a very, very stable, very, very certain range of temperatures. So it's a few degrees, maybe 2-3 degrees, around 37 degrees where we can function, and then our body systems are damaged if we go above or below that. Compared to that, reptiles are ectothermic, which means their body heat comes from outside, and all of their body functions are designed to vary with the varying outside temperatures, which influence the variation of the inside temperatures. So you might know these as cold-blooded animals. We don't really use that term much, and that's because it's not really the warm or cold, but it's the source of the heat and the range of temperatures. So in these pictures, these are thermal images, which are visualizations of temperature. So here, this is the same chameleon. Do you see the chameleon? Okay, so these are two chameleons, and you can see that the cold temperatures, that's the blue and green. In the blue and green, which are cold temperatures, you see the chameleon has the same body temperature, and in the red, in the hot temperatures, the chameleon has a hot body temperature. So it eventually reaches an equilibrium of its body temperature with the outside temperature. And even in cases where you have a hot reptile in a cold environment, like this skink in this picture, it's not because it generates heat, but it just went to a sunny place or to a warm rock, gathered heat, warmed itself up, and then shuttled back to the cold place where it could function in the cold region with a warmer body temperature. But eventually it would reach equilibrium and have to do it back and forth again and again and again. So going back to the snake in the snow, what would happen to it? It won't start dancing, and not just because it doesn't have legs, but it's the environmental temperature will influence its body temperature just by very simple passive heat exchange. And then the body temperature influences the energy use by all the energy consuming and energy producing processes in the body, because all the enzymes in the body that carry most of the enzymes, ask me about it later, it's irrelevant. Most of the enzymes are, their function is temperature dependent. And the functions that they carry are therefore within a certain range, between certain limits. The function increases with the temperature, and that influences the rate of all the functions, which could be growth and development and brain function and reproduction and basically running speed, anything, any functions of the animal. And that's this direct link which we as endotherms don't have, because the first link, we've broken it by burning energy to heat ourselves. They have this direct link between environmental temperature and their function. So scientists have taken this direct link to calculate and predict many things. For example, responses to climate change. They say, okay, we know, or we can predict a certain change in environmental temperature. How will this downstream affect their function? And there are models, and this is treated basically as a physical, predictable, even mathematical thing, like a pot with water on a stove. If you know the temperature, you know the rate of the water heating. And my question is, how predictable is it, or how passive is it? Are these red arrows influenced by the animal itself? Does it have control, or does do these direct links, which we know are direct, does the link change in its characteristics between different times and places? So the questions are divided into basically two aspects. So the first one is, how does the body temperature dependence on the environment change in different times and between different places, and how does the effect of body temperature on the energy use, on what we call the metabolic rate, how does it change in different times and in different places? So what's the rationale behind this? Why would I even think that it should differ, because it's treated as sort of a passing thing? Why would 20 degrees in one place not be the same as 20 degrees in the other place? And that makes ecological sense, because 20 degrees do not mean the same thing for a reptile in different places. So, for example, in winter, when it's cold and it reaches 20 degrees, that's the hottest it's gonna get. That's your chance to go out and gather heat and do everything that you need to do before it starts freezing again. Whereas in summer, that you wouldn't spend your time thermoregulating, basking in the sun in 20 degrees when you can go and do other stuff. It's gonna get hotter. Or when it gets too cold, in places that have colder winters, for example, even the Israeli winter, when it gets to 12 degrees during the day, there's no reason to go out and be active, because even if they can be active, as I said, they'll be slow, like the snake in the snow. They'll be slower than they would have been, so they won't be able to catch enough food. So it's better to just stay in shelter and not use any energy, or not use any extra energy. And if you're not using any extra energy, why not use even less and not waste the little bit that you are using? So that's the idea behind it. And same goes for differences between day and night. If you're not going to be active at night, then it doesn't matter if it's the same temperature. Maybe you can save more. And the same goes for different regions which have different climates. So, for example, this Chardon Matsui, this is the Laudakia vulgaris. It's the same species in the north of Israel and the south of Israel, but it wants to have more or less the same function. It's the same species and it has a similar life history, but one region is much hotter than the other one. One region experiences much more extreme temperatures, so it might want to compensate by having a lower energy usage on a regular basis, and then with the hotter temperature, it will eventually reach the same energy use as its northern counterpart. And this is known from different animals, but not in reptiles, and not really compared between different species. And these questions are starting to get really vast. We have different species, or the same species, or different times, or different. So the way that we tackle this question is by doing a comparative study, taking as many animals as we can, treating them to the same different conditions, and seeing how different species react, how the same species reacts between climates, how the same individual reacts between seasons. And Israel is a great place to do this kind of comparative study, because we have 82 species of squamates. There's reptiles and lizards. We have almost 100 reptiles from 16 families of squamates. That is 1% of the total reptiles in the world. That's a lot for to have in such a small geographic range. So we can compare them in a very restricted range across a broad genetic and evolutionary divergence. And that's also almost a quarter of the representatives of almost a quarter of the reptile families in the world. So what do we actually do? I go out to the field and I collect these animals. I either do an experiment in the field, or I bring it to the lab and then take it back again. And finding the animals can be very tricky. So it might be following their tracks in the sand for hours until we find the animal. That's what I've been doing over the last 4 days before it started raining. It can be trying to get them out of some hiding place where they've been hiding, which can be difficult, which can sometimes be very difficult if they're up in the tree. We caught the snake in the end. And sometimes, you know, if you're lucky, they just crawl into your lab and you can pick them up and measure them and release them. But that's an exception that's happened. So when I catch them, these are pictures of, just to show you the diversity of animals that we found. These pictures were all taken either by me or my lab members in these trips. When we have these animals, what do I do with them? So the first thing and the simplest thing and the most common thing I do is just very simply measure their body temperature. I catch the animal, I take a thermometer, I stick it up there. I need to get a very accurate measure of their body temperature. And we've done this for many species all across Israel. This is all the places we've measured them. We capture a very broad range of climates that we have inside Israel. But Israel has a wide range of climates, but not a very extreme range of climates. So we thought maybe we'll start contacting my supervisor's friends and people that I've met in conferences, and it started expanding. And we ended up having data, people repeating the same measurements all over the world, and we've gotten to 15,000 individual measurements of almost 200 species by now, from 25 different countries, 50 different scientists, and this allows for some very terrifying statistics to be done and interesting conclusions to be taken. The metabolic measurement is something that I've been doing just myself, not with all these collaborators, but for 54, which is the majority of the Israeli species, catching them, bringing to the lab, measuring them, and then releasing them. What I measure is the metabolic rate, the energy use, which I can approximate by the oxygen consumption. I put the animal in this incubator, waiting for it to go to sleep. When it's asleep, and we can see that the respiration is very, very stable, and we got to the lowest, most basal metabolic rates, and the animal starts just breathing at a constant rate. When it breathes, we know how much oxygen came in, and we know how much oxygen came out, and we can get this graph of how much oxygen the animal consumed, and thus we know its metabolic rate, and we can compare this, the same animal, at different seasons, between regions, between species, and start to get a general idea of the differences. So just very broadly, I'll tell you that we find the same two basic principles repeating themselves between species and within species, which is that if the temperatures get cold, they compensate, they manage to counteract physiologically the adverse effects the temperature would have had. They go and they thermoregulate more, and they become more efficient at thermoregulating, and their metabolic rates become higher to compensate for the lower temperatures. But if it gets too cold and they're not going to be active, and they know that they're not going to be active for a long time, winter, they know that for 3 months they won't have suitable temperatures for activity. So what they do the exact opposite. They don't counteract the effects of temperature, but they enhance the effect of temperature. They don't just lower it passively, they lower their metabolic rate well below what it would have been even with these cold temperatures. And in that way, they can conserve energy in a period where they don't eat and they can't gather new energy. And then they emerge in spring with more available energy. So in general, we see that reptiles are not a pot sitting on the stove and passively just exchanging heat. They have all these incredible metabolic, physiological, behavioral adaptations that allow them to not be affected by the cold. So these are adaptations that I don't have, so that's why I'm gonna need my scarf back. So yeah, that's it. Thank you very much. I'll be happy to take questions.
Very nice talk. So Again, all from the Weizmann Institute. So what do we know about the time scale for this adaptation? So how much it takes for these adaptations to happen, and what can we draw about the biological mechanisms that create these differences? Like if we think about a specific species, or if you take like a
So
chardon from the north and a chardon from
when
the
you say
south.
adaptations, you mean the evolutionary adaptation of the species over the years, or do you mean the acclimation of the same individual in a certain year?
Yeah, so I'm asking about how much of the differences that you see is coming from things that are large, like long scale, which is, I guess, like genetic or epigenetic, and things that are much smaller scales, like adaptations of things in the body.
So what I do is, when I have many species in the same analysis, I I run physiological analysis, which means that I correct for, and sorry for the statistics now, but I correct for the relationship. So instead of assuming for a certain statistical test a normal distribution or random differences, what I assume is that the differences would change with the evolutionary tree that I have of the relationships, and then I can see the changes with climate, or the changes with anything that I compare, body size, activity pattern. I can see how they changed, even assuming that the large scale adaptations will take place between the species. And then when I have the same species, I can see how long it takes for it to change. I can measure one species exactly when winter starts, and then 1 month afterwards, and then 2 months afterwards. And different processes follow different patterns. So some of them would start before the winter as preparation. Some of them would start immediately with winter as a reaction, and some of them would just gradually gradually change throughout the winter as a secondary effect. Hope that answered it.
So thank you, Shahar. It was really fascinating. Can you hear me well? Can you hear me?
Yes.
Okay. Thank you. It was really fascinating. So my question is, we all know and we feel it with ourselves that the seasons are changing. And I wanted to ask you about this specific moment of doing this research, because as you know, you can get very hot days in the winter or an extremely hot summer. Can it affect the reverse compensation, and in what ways? And also another question relating to the change of the seasons, for example, with energy consumption. So if you're a reptile and you wake up in the middle of the winter, you know, very energetic because the days are getting hotter, but you don't have what to eat. So like, if you can say something about that. Thank you.
So yeah, this winter was incredibly short. We managed to get almost nothing done, and we had a joke that we can have a control of a year without a winter and a year with a winter and compare them. But from activity surveys that I've done on a species, not the actual physiological things I showed, just seeing when they are active, we saw that even when we had really hot days during the winter in places like in Gedi, so it got to, you know, really hot, really activity facilitating temperatures, the geckos that we looked at weren't active. So they stopped being active in the beginning of December, and they were inactive until last week. And that shows that it might be part of this physiological mechanism, because it might say, okay, it's a warm day now. It might be a warm 2 days or 3 days, but my internal clock maybe tells me that it's still winter. So from what the organism knows, it's gonna get cold again even if it's hot. And if it gets cold again, it has food in its stomach, it's not gonna be able to digest it. That's even, that's a peril for its life. So it's not gonna eat, and then therefore it's not gonna come out, and that's why we don't see them active even when it gets hot. Which, you know, also relates to your second question, because if it gets hotter and they are not active and they're not getting the extra energy that they need, but they are passively losing more energy than they would, then they might emerge with less fat than they would have had, and they emerge with a lower body condition. But then again, the winter ends earlier. Like they went out now. They know that winter is over. They're not fooled by this rain. So there is no way to really calculate how climate change would affect it, but the physiology should be incorporated into the current predictions, which just treat it as completely passive. So, yeah.
Shahar Dubiner, thank you very much.